Now, before moving on, we need to discuss two more important elements that affect earth pressure: cohesion and water table effects. We'll start with cohesion. And because we don't do extensive soil testing, we don't usually account for cohesion on our standard bridge designs. However, it is usually a common assumption that gravelly and sandy or coarse-grained soils don't have any cohesive properties. Cohesive soils, like clays and other fine-grained soils, behave less intuitively. Instead of just relying on grain-to-grain friction for shear strength, like coarse-grained soils, they have cohesion due to water in the pores. And because of this water in the pores, they're also subject to consolidation and long-term settlement, as water gets squeezed out of the pores. And I've shown in a example for you here, some external pressure P can compress this block of soil and squeeze water out of the pores, and this can happen over the course of many years, resulting in settlement of the structure. So I'm going to go into how cohesion would affect our design example from before. And I've drawn this all out here for you. And first, the active earth pressure coefficient, Ka, will change due to cohesion. This is subtracted from the original value because cohesion decreases the amount of vertical pressure that translates to horizontal pressures. It also decreases the area pressure load term by subtracting another cohesion term. And this makes sense, right? Because the cohesion is going to keep the soil together. It is less likely in an active pressure situation to want to fail and slide onto the retaining wall. It's going to put less pressure on the retaining wall because it has its cohesive properties. So then the active resultant can be computed as normal using a triangular distribution. But I want to point out especially that I put this in terms, this Ka prime, this new Ka in terms of the old one, so you could see how the cohesion term would subtract out. And then also it would be subtracted in the pressure distribution term. The cohesion affects how much pressure is being distributed onto the fictitious retaining wall in this case. So next I'm going to talk about the water table. If water table is present, the unit weight term, gamma, has to be taken as the effective unit weight, which is the saturated unit weight minus the unit weight of water. I like to think of this as the water is creating a buoyant pressure on the soil particles, reducing their overall weight. And then we also need to add a pore pressure term to represent the lateral pressure from water. So while it's reducing the soil weight, there is water table present that is also creating a lateral pressure on our retaining wall in this case. So it would affect our design example as follows. So in calculating our active resultant, we now have three different distributions we're looking at. First, we're going to be looking at our dry unit weight of the soil. That is discussed in the previous design example. Everything is going to be normal. And then when we get to the depth of the water table, it is going to continue vertically and create this rectangular distribution of lateral pressure on the retaining wall. And second, we have our modified active earth pressure that is going to be a function of our gamma prime, our effective unit weight. So from the water table down to the base of the wall, we now have a reduced unit weight because of the pore pressure from water. And then third, we need to finally add on our triangular distribution of pore pressure from the water. Which is based on depth. We have our unit weight of water multiplied by its depth to add that pore pressure. So these three different terms, or four terms really, but three different situations, add together as follows. We have our normal, if you will, dry unit weight, and then we have that as it continues as a surcharge load to the bit of the retaining wall below the water table. Then we have our effective unit weight creating a active earth pressure on the retaining wall, followed by our pore pressure. And this is how they would all combine together in a situation in which the water table is up above the base of the retaining wall or bridge abutment.